Okay, so let's pick up kind of our half social studies class, half physics class. You actually do need to know a lot of the scientists and their accomplishments. I spent some time on the weekend. I don't know if you guys noticed, but I took the timeline off of that board and I put it over on the sidewall over there because I think that might be useful for you to kind of know the different accomplishments through history. So just to kind of recap, Sir Isaac Newton thinks light's a particle. And they had good evidence to think light's a particle. And then after Sir Isaac Newton dies, then some scientists are finally brave enough to kind of challenge the conceived notions of the day and say, but I have evidence that light doesn't just bounce off of things, it also seems to do other weird properties. And so that's where I'm beginning this topic right here, is Newton's particle model for light was eventually replaced by a wave model. And there are three concepts and experiments I want to show you today that helped pave the way for light to be considered a wave as well. So here's the first one. It's the principle of diffraction. This is Huygens' principle of diffraction, where we recognize that waves will actually spread out after going around or through an object. And I tried to illustrate this to you guys in class before, but maybe why don't I start with this photo right here. I think this one right here illustrates using water waves exactly how we know that waves spread out. If you were to have water going through this spillway, this dam, or whatever you're calling it right here, can you guys all literally see how the wave front, oh, you can't even see purple. Let's use yellow. Can you guys see how the wave front is spreading out in a circle? Which is good, because if it didn't do that, there would be no water over there on that side, and there'd be no water over there on that side. If you somehow assumed that water would only ever keep going along this like bowling alley trajectory, we recognize that that's not how it's going to work, right? We know that it's going to want to start spreading out, which is why we can have water over here in this corner. Light does the exact same thing to some degree. Light has the ability to bend around corners. I mean, imagine that I were to open up just one of these windows right here. Does light only go through just to there? Would we be sitting in the dark over here if I opened up this window and let light come through as one big thing? Well, no. Light's going to go kind of around the corners, and it wouldn't be dark over here. It wouldn't be like the most brightly shone spot, because straight on would obviously be better, but light has this ability to spread out. And so we can actually demonstrate that as a wave, and I've got some evidence for that in a bit, but does this kind of make sense, the idea of how it's going to spread out around a corner? It's not going to happen instantaneously, but eventually, yeah, light will then show up over here. It might reflect off of something, and now all of a sudden this corner over here has some light. Not as much as right here does, but... just for some more pictures before I get to one of the most famous experiments we're going to show. This is pictures showing wavefronts. And so if I haven't explained this well enough before, imagine you had a candle. The way we would explain this then is that a wave is going up and down and up and down and up and down and up and down. But is there actually anything going up and down and up and down? No, we don't even need a medium for waves to travel through, but I think the best way of us trying to explain this is to try to think of a mechanical wave that's going up and down and up and down. Think of an actual physical wave that's going up and down, and then just transpose that picture into your head and imagine that wave fronts are going up, back and forth like this, and then the wave is basically moving outwards. And so light out of this candle is emanating in all 360 degrees. On our timeline, and again, we need to know this timeline stuff, so don't like glaze over it going, Chris, I don't need to know dates and people. We might. We likely will, actually. One of the most famous experiments was Young's double slit experiment. It was in 1801. And through this experiment, Young managed to prove that, that light isn't just a particle. Here's how the experiment worked, and then I'm going to show you a couple of YouTube videos on it because I don't have the apparatus to do this well. But what he basically did is he shot light towards a screen. And when he shot it towards the screen, he put just two little holes in the screen. And if Newton's model of light was correct, and light is a particle, you would expect that some light would make it through just the one slit, and then there'd be a beam of light over here. You'd expect some light would go through here, there'd be a beam of light over here, and that's it. That's what you would expect if light was a particle. But I've kind of already spoiled the ending to this one. We know that light doesn't just act as a particle. This is what actually happened. And so when Young did his double slit experiment, as he shot light through these two little slits right here, what ended up happening is he got this crazy pattern where it basically went some light, then nothing, then some light, then nothing. And what that seemed to infer then is that light had this ability to bend in all directions, and it really had the ability to spread out. One of the weirdest things, actually, is that light ended up right here, the least likely spot that you would expect for it to be, because this location right here would be dead center in the middle of those two slits, right? Like imagine that you were throwing an object, and sometimes you threw the object through the one slit and through the other slit. You would expect that particles would go here and here. Well, what ended up happening in Young's double slit experiment is that light actually ended up right in the middle. It's almost as though it somehow managed to go right through the middle right here. And this confirmed evidence that not only does light have the ability to diffract and to start to go out in wave fronts, which then explains why the heck we have light way over here, and if it also went way over here as well, why you'd have light over here, but it also confirmed a principle known as interference. And that's what's happening in this kind of schematic diagram. This is what scientists, again, believe is occurring, because it's not like we can actually go on the magic school bus, zoom down to size, and actually look at what's there. There's nothing to look at. Right? But this is what we believe would be happening, is that as light came through this opening right here, it began to diffract. And as it diffracted, it spread out slowly but surely. And as it went through the second opening right here, it also diffracted. And what happens is that at each of these times right here where there's overlap, each of these locations here, you have what's known as constructive interference. Now, I didn't teach you guys in Physics 20, but are you familiar with the concept of construction interference? Okay, a few of you are nodding. I've got a few slides to discuss this. This slide right here, I think, helps explain it best. If you have two waves that are completely in phase, where the trough meets trough, the crest meets crest, right? So trough's down here, crest is up here. If they're completely in phase, then what ends up happening is these two troughs, they add and become even deeper. And these two crests, they add and become even stronger. That's called constructive interference, right? If waves are in sync. Resonance is an example of waves being in sync. But if you have them being out of sync, then they completely interfere with each other and they destroy each other. Well, if I can go back to this example right here, what this would then suggest is that at certain points when waves are emanating outwards from a certain source, there are certain spots where you have like a peak. And then there's other spots where you have nothing. The nothing spots are where you have destructive interference. The peaks are where you get extra waves. The example that I think of when I think of this is in the summer times, my parents have a cabin out at the lake. And there's a small lake, but there's more than enough room for a bunch of boats to be out there. Any of you guys ever do boating in the summertime, like water skiing or wakeboarding? If there's one boat out on the lake, it's not so bad. But as soon as you start to get 2 or 3 or 4 boats out on the lake, sometimes you get some pretty decent waves, which if you're water skiing, we don't like waves when you're water skiing, but if you're wakeboarding and you want to get some air to jump off of, you kind of like that a little bit, because if there's lots of waves kind of rumbling out there on the lake, sometimes those waves are going to build on each other, and you're going to have this scenario here where you get even bigger waves. And there's going to be other times where the waves don't build on each other, you get nothing, but that's better than this, right? Here you just have just a normal wave. If you have a second boat out on the lake and it produces some more waves, they could become in sync, and you get some pretty awesome waves to kind of jump over. The people who go doing ski-doing, like with the jet ski, they'll often add way more waves because they're in sync. So, okay. This actually is the same principle as to why sometimes different devices will sometimes cause interference. I recognize this in my house. Because I have little kids, we have a baby monitor that runs on like, I don't know, 5 gigahertz signal or something like that. And what's interesting is if we ever run the microwave, our baby monitor stops working. It's fascinating. I did a little experiment because I was curious in my house, but if I turn on the microwave, my baby monitor stops working. And the reason why is that they must be running on a similar enough frequency that when the baby monitor is oscillating at this frequency, and the microwave is oscillating at this frequency, they cancel each other out, and the signal gets blocked, basically. So, why don't I show you some YouTube videos now? Because as good as I am trying to explain things, it works a little better, I think, if I've got a pre-made video. So let's watch a few different videos that I've got that will hopefully illustrate even better. Let's start with this one. This is going to explain Young's double slit experiment again.
Young's double slit experiment. Interference in light waves from two sources was first demonstrated by Thomas Young in 1801. The schematic diagram of the experimental setup is shown here. Light was made to pass through a slit SO. The wave emerging from this slit was made to pass through two.
So this would be like a wave front, right? Highs and lows.
These two slits served as a pair of coherent line sources because waves emerging from them originate from the same wave front and therefore maintain a constant.
And that's probably a good place to stop here. So what's supposed to happen here is as this wave front goes through here, you can see you get smaller and smaller and smaller little wave fronts here, smaller and smaller small little wave fronts here. But at certain sections, they're going to overlap. And so right here, there's been positive overlapping as like a crest meets a crest, and you get a really bright spot. And as that kind of keeps working out here, what ends up happening is as like this one keeps going like this, and the other one goes the other way, there's certain spots where the positive overlap occurs, and that's why you get this bright fringe right here. But at the same time, you also get that destructive interference, and so right here you get like a crest meets a trough, and then you get dark fringes. And that's actually what's happening in this example right here. When I shot a single light source through here, when I run it through this right here, we're actually seeing light interfering with itself. And so see how right here, I'm going to try to keep this steady. Right here is where I'm going to try to aim the light with my laser pointer. As soon as I put this in front, this will be the one spot where, hopefully if this works well, where I actually won't get any light. Oh, no, it still did work there. Oh, well. But can you guys see how you've got all these dots that are in sequence like that? That's this pattern right here. Bright, dark, bright, dark, bright, dark. So I was hoping it would be offset, but it's not. I guess it's because I'm not using a double fringe. I'm using like a multiple double fringe. So that's actually what this thing here is doing. It's actually, rather than having just two slits, it basically has like 1,000 of them. And if you have 1,000 of them, you get way more interference because things interfere with itself like, I don't know, exponentially almost in a way. Yeah, Sean?
Why does the light bend inward after the second barrier?
Through the second barrier? Oh, like this one right here? I don't know why they've drawn it. Like, I get what you're saying. Like, why is it not going straight there? I don't know why they drew that way, to be honest. Yeah. That's not usually how I see the diagram being drawn. Let me go back in my notes here. Because normally the picture looks more like... Where's our notes again? Normally the picture looks more like this, where you can kind of see that it kind of kept that concentric half circle going evenly there. So I'm not actually sure why they drew it quite like that in that diagram. Let me show you another video here, because that first one there is a little dry. This guy right here does a lot of good science videos, and I like this one. Hopefully this will help explain things. This is a longer one. I'll play the whole thing.
What is light? What is light? Light, what is light? What is light? Light is brightness, I guess. Yeah, or which are light?
It lights up the room. It makes it not dark.
What's the difference between blue light and red light? Come on. It's in your eyes and then you see stuff.
White is made to orange to green at the top of the body.
Can you see my aura?
No, particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me. What light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens experiment I've recreated today. Thomas Young's double slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
That's so cool.
This is about 1/30th of an inch, right? And observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes, small dimensions. This is an experiment so simple that you can make it at home, and yet so fiddly that I have never seen it before done with sunlight. I was thinking about doing it in a box, like a fridge box, taking it out of the street.
This guy had a brilliant idea.
We're doing a science experiment.
Just brought a fridge box with him.
And this is a little eyepiece so we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings, very narrow openings side by side. It's a double slit. And before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom? The most thing is you think we're going to see two lines. Two lines in the bottom of the box. Two bright bands.
Yeah, I think it'll be one line for two.
I think it's the whole box it up.
That's going to be collaborative.
A bunch of colors.
Probably, yeah.
Right on? Colors. Yeah. You expected to see kind of one line. Is that what you see?
No.
I see dots.
And one circle.
Well, there's one in the middle strongest, two out of phase that's going outside of multicolored. One in the middle, which is one.
Kind of a rainbow.
The rainbow color as well. Quite a few colors, but lots of little dots. There are more dots in there. I think I can see more dots. Spreading along. Yeah, absolutely. So I can see kind of the dots now. Not tons, but I can see dots spreading. Like that way. Yeah, definitely. Isn't that amazing? Yeah, that's incredible. And that's just nothing else apart from two slits.
This is hat backwards.
That's incredible. So all we're doing is we're putting a light through two very narrow slits side by side. How does this make any sense? There's some kind of principle involved in it. The average person's not familiar with the explanation. No, I'm really confused by it, but I'd like to find out why. People were debating, is light a wave or is it made of particles? So what caused that? Well, if light were behaving as particles, you would expect it to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the waves from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting
I'll give it a little bit further. Can you guys start to see where the bright spots and the dark spots are going to start to align here? Right. Like, there's almost like a line going right about here, and right about here, and right about here. You guys can actually visually see that. He hasn't even altered the video yet. This is actually like just the overhead camera, right? He's going to put an overlay on top of it, but you can kind of see where the waves are still kind of big right here, here, and here. But you can also see where the interference is otherwise.
This pattern is created by the ripples from the two sources interacting with each other. Where they lead us peaks with peaks and troughs with troughs.
Yeah, this is a good
the
one.
amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is a
So I know they're now manipulating this, right? So now the shot has been manipulated, but you can see that right here where they're making this brighter, that was actually the opposite, right? Let me replay that for 30 seconds, because that's the destructive interference he's just shown here. Right here, and right here, and right there, that's your destructive.
peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave. wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the tip of the wave from the other slit, you would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
Same kind of concept, eh?
As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and a bright spot, and a dark spot, and a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what causes the rainbowing effect as you go further from the central maximum. But even though the ones to the right were slightly colored, that's not the point. The reds are going to meet up at different places than the blues. And that's all the basic color differences, different wavelengths. Exactly. That's amazing. So the difference between the red and over there, the green spot is just, I'm seeing it.
He just blew this guy's mind, eh? That's my joke. All right. So hopefully that video kind of explains it, I don't know, in more detail. I do need to move on because there's really a couple parts to this lesson today. One of the parts is trying to explain the history, the idea of the whole point of the double slit experiment was to try to figure out whether light was a wave or a particle. I've already kind of spoiled the ending, but we actually know the answer is that it's both. Light is actually both exhibiting particle and wave properties, but at this point in history, they now managed to prove that light could be a wave. Okay, and it was pretty conclusive. Like Young's double slit experiment more or less solidified the fact that it has wave properties. The question then became, okay, if we now know that it has wave properties, are there some formulas that we can use in order to do some math? Because, I mean, one of the hallmarks of physics is we should be able to make conclusive predictions every single time as to how things are going to mathematically work. So there are two formulas that we use when we talk about the interference of waves on top of each other. Here are the two formulas. One of them solves for the wavelength, and it's going to tell you X, D, and an L. And it's a pain to remember what each one of these letters means. So we're going to do a lab on this next week to try to help solidify which one is which. But if you were to imagine that, I were to redraw kind of the experiment. Imagine that light was coming through these two holes, and then it was emanating outwards, right? And so it starts to interfere with itself, it starts to interfere. And eventually over here on the side wall, you then start to get that pattern of light and dark fringes. Okay. Here's what all these variables mean. Okay. First of all, wavelength is the wavelength of light used. Okay. Because you have to shoot light, right? Like light has to be shot through the two openings here. So wavelength is what variety of light are you using? Are you using red light, yellow light? White light is all of the colors combined. So that's one. X in either of these formulas, which I guess is just the top one here, X is how far from the central fringe. So can you see how right here, this is actually the spot that people thought was going to be the least likely for there to be light, which would be right in the middle of where the two gaps are right here. This is known as your central fringe. And we often denote it with 0 because it's like the middle of everything and it goes symmetrical around it. Okay. If you ever see the letter N, N in this formula here refers to how many fringes away there are. So right here you have your first fringe, there you have your second fringes, here you have your third fringes, and so on. You actually have 2 3s and 2 2s and 2 1s because there's one on either side as it interferes with each other. Okay. I should move on. I'll do the demo of that one again later. So that's what N stands for, is how many fringes away you are. L stands for how far away you are from the screen. And so if you shoot the light from here to here, L would be basically how far away you are. And so if you bring something closer or further, it changes the geometry. What have I missed? D. D is how far these two slits are apart from each other. This is D. So if these two slits are like 1 millimeter apart or 10 millimeters apart, that's the distance between the two double slits that you've got there. If you use this formula down here, the angle theta basically would be like, if I were to go say to the third fringe right here, this would have been straight on, but light deviated to the third fringe right here. This right here would be theta. It would be the angle with the normal, right? See how this right here would be a 90-degree straight on angle? The angle compared to normal would be this theta right here. And so these formulas are not overly hard to work with. You just have to remember just which variables go where. Okay? These are not likely to be part of like a long string of formulas. You more or less just use them as a one-off. Okay. There's one more thing I need to let you know. It's that this top formula, and I can maybe explain this another time if you'd like, but this top formula is actually an abbreviation of the bottom formula. The bottom formula is the correct one. It's the one that if you'd like me to explain where it came from, I can, but it's going to take a little while. But the bottom one's the correct one. What they've done, though, is you know how sine is usually equal to opposite over hypotenuse? Sine is opposite over hypotenuse. Well, not D to L, X to L, X and L are effectively what your opposite and hypotenuses are, except X is how far it is right here. That is an opposite, right? But L was actually this side right here. And the hypotenuse in this triangle should have been this side right here. And so it would work better if it was tan, because you know how tan is opposite over adjacent? X and L are really close. And because the distance is really far away, you can use an approximation and basically assume that if sine of theta is opposite over hypotenuse, this length right here is more or less this length right here. Like, they're going to be relatively far distances, but we know the hypotenuse is always a little bit more. Long story short, this formula right here is actually an approximation. It is not going to be perfect. The bottom formula is by far the better formula to use, but if you would like to, we're allowed to approximate with this one right here. But if you understand my rationale, sine was supposed to be opposite over hypotenuse, which should have been this x value divided by this length right here, which is the hypotenuse length. But that's going to be really close to this length right here, the actual distance in the straight line. So that's why we're allowed to approximate this. Okay, let's try some math examples. Suppose you have some yellow light. Yellow light has a a wavelength of 540 nanometers. You slide it on the double slit with 2.2 micrometers apart. Let's figure out the angle to see the second order fringe. Okay. So if you're looking for an angle, it means we'll use the second of the two formulas. So wavelength is equal to, what's the formula again? D sine theta over n. I have all the values we're looking for. You just need to plug them into the right spots. This right here is a wavelength. It's going to go into that value there. The 2.2 micrometers apart is the distance between the two slits. If you want the second order fringe, that means that this number right here needs to be 2. By the way, why can't we do this for the central fringe? What would the angle be for the central fringe? Nothing, yeah, right? First of all, you can't divide by 0, but would there even be an angle to the central fringe? I mean, there is no angle if it goes to the central fringe, right? You'd have to have an angle to go to the first fringe or to the second fringe, so you can't even do it for the central maximum one, right? The one that goes like right between the two dots, the two fringes. So, anyways, let's plug in some values. We do need to, though, make sure that we use units properly. So here's how I'm going to do this. I'm going to make this 540 times 10 to the minus 9 for my wavelength, because this was in nanometers, and a nanometer is to the minus 9. D, yeah, we want them to be in consistent units, if we could. So let's just put them in meters all the time. D right here, the distance between the two cuts in the little frame there, was 2.2 micrometers. So a micrometer is to the minus 6. And we're going to divide this all by 2. So all you guys need to be able to do is just isolate this and solve for theta. So the way you're going to do that is you're going to take the sine inverse of 2 times 540 to the minus 9 and divide it by 220 to the minus 6. And that'll give you what angle this light has then bent through. Make sure you're in degrees, by the way. 2 times 540 times 10 to the minus 9 divided by 220 times 10 to the minus 6. I got 29 degrees. Okay. So if I could re-demonstrate that, what's happening here, I can't do the double slit experiment, but this is basically a whole bunch of double slits, if that makes sense. There are 100 lines for every millimeter on this diffraction grating, so there are many different lines all cut inside of there. And so there's lots of interference happening. What that would mean is that if I were to shine this right here, let's shine it on the dot right here. This is where normally the central maximum would be. If I then run it through here, then if I were to like plot where all of these dots are, the angle to the second dot, let's stick with this one here, the angle to the dot that shows up over here, because that would be the second dot, right? Right about here's the first dot, there's the second dot. The angle to that second dot would have been 29 degrees, right? The angle to the third dot would be even bigger. The angle to the fourth dot would be even larger. Does that make sense? Okay, let's move on, because I got more stuff I got to get to, and I got 15 minutes. Okay, let's do, I think I have one more example on this. Let's say that we have a couple of screens placed 13.7 meters apart, and I'm going to give you a third order fringe. This screen is 2.5 centimeters away from the central fringe. I'm going to give you the slit's distance. Let's find the wavelength of light. Okay. This is the other of the two formulas. So the two formulas were the wavelength equaled the sine formula. This is the proper formula, but we're allowed to use the approximation formula if we'd like to, which is, I believe, I always forget. I have to remind myself. It's xd over nl. And so you got all these different variables. You just got to keep track of which one is which. Okay. So if I can kind of draw this again, let's say that you have this double slit. Light starts to bend through one of them. Light starts to bend through the other one. And then eventually over here on the screen, here is your central maximum. Then you get your number 1 dot, you get your number 2 dot, you get your number 3 dot. In the opposite direction, you get the exact same thing. So that's kind of your picture here, if that helps gives you a visual of how this is starting to interfere. Here's what we know. The two screens are 13.7 meters apart. So that means from there to there is 13.7 meters. I can't see very well. I gotta move back here again. So it's 13 centimeters to the whiteboard, effectively. The third order fringe is what we're looking for. So we're looking for this third order fringe. And I know that from here to here, from the third order to the central fringe was 2.5 centimeters. That's what's been given as well. It tells you that the slits right here, the distance between these slits right here, are 9.60 times 10 to the minus 2 centimeters between them. And so we just got to figure out which numbers go where in my formula. Okay, so x is how far away this is right here. So I'm going to put 2.5 centimeters right here, but I'm going to make it 2.5 times 10 to the minus 2 because I need it to be in centimeters. Or I need it to not be in centimeters, I need it to be in meters. So that's what x is, the distance from like one dot to the next dot, basically. D is the distance between these slits right here. So this number right here needs to be the 9.60, but I'm going to make it times 10 to the minus 4. Why did I make it times 10 to the minus 4? Yeah, because it's in centimeters and it's already to the minus 2, so I'm adding an extra 2 onto that. Okay. N is the fringe we're using, which is the third order fringe, and L is the distance from here to here. So from here to here was 13.7 meters. Okay. So you guys can probably type all that in your calculator. I just want to redraw and show you why this approximation is allowed to work. It has to do with the triangle right here. It was supposed to involve an angle right here, the original formula, and it was supposed to be the sine of the angle, which would have been the opposite compared to the hypotenuse. Well, the opposite is what we call x in our formula right here. This opposite side right here is what x is. Now, this hypotenuse right here, we don't know this hypotenuse, but we do know that this hypotenuse is roughly the same as this distance right here, which we call L. So because this hypotenuse is almost the same as L, we're allowed to use this approximation. It's close enough. So, did any of you guys get an answer? 8.4 times 10 to the minus 7. Okay. If you guys got 5.84 to the minus 7, what I was hoping to hear was the minus 7. And the reason why is that most light is in the nanometers range. And to the minus 7, if the decimal places right here, makes sense because this is actually 584 to the minus 9. Because what I'm really doing is I'm moving the decimal place over 2 more times. But as a consequence of moving the decimal place over 2 more times, it's now to the minus 9. And then a minus 9 makes it a nanometer. Which is what I was expecting, because most light falls between 400 and 700 nanometers. If you weren't aware, 700 to 750 nanometers is red light, and 400 nanometers is about purple. So this would actually make sense here. Any questions? Okay, let me move on. I got 10 minutes left. I should be able to finish pretty reasonably here. This is a picture of what I actually have. I don't have a way of doing a really good double slit. That's why I showed the video of the one guy, because he did a great job of it, making that big cardboard box device. I don't have a double slit, but I have a diffraction grating, which is basically a whole bunch of double slits. What ends up happening is there's a hole here, and here, and here, and here, and here, and there's like 1,000 holes in that little cardboard slide I had right there. And it just causes a ton of interference, because there's some between these ones right here that interfere, but there's also interference between these holes right here and those ones. Basically, interference happens like everywhere, right? And you still end up with the same pattern. You end up with a bright spot, another bright spot, another bright spot, another bright spot. The math works a bit differently, because when I'm shooting this through right here, that central one, it still does show up there, but you still use the same formulas. Okay. So I've got one more example here. I'm telling you now that the diffraction grating has 100 lines per centimeter. I'm going to tell you how far away the screen is. I'm going to tell you it's a first order fringe, and I'm going to tell you how far it is away from the central spot right here. It wants to know what's the wavelength of the light. So, by the way, if I use the word antinode, do you guys know what the word antinode means? If I were to give you a wave function like this, where are the nodes? Yeah, these are on the axis. Whereas the antinodes are here and here and here and here. They're your crests and troughs. So the antinode then, the central antinode, is the first place where you have that constructive interference, where it interferes with each other. So if I ever say central antinode, it basically just means it's that middle dot here. So let's try the exact same formula again. The wavelength formula we just learned was, what was it, xd over nl. It's the same formula. Let's plug in some numbers. I'll leave 1 for last. So I'm gonna leave d for last. Let's talk about x. Which of these numbers that's been given up here is the x value? It's the 19.2. Because what it said here is that from the 0 fringe to the 1 fringe to the 2, and then the same thing right here, it's 19.2 centimeters between one dot to the next. So if I were to shine my laser pointer on the wall again and measure the distance from the middle one to the first one, that's 19.2. So this d value here is going to be 19.2 to the minus 2, because it was in centimeters. We wanted to do the first order light fringe, and I don't care whether you go to the left or if you go to the right, the math's going to be the same either way, right? It's symmetrical. So n needs to be 1. The length is basically how far the light traveled. So as the light traveled from like one spot to the next, that's your distance away. If I could illustrate that with my laser pointer again, watch what happens if I shoot the light through from here, or if I then come closer. Can you see how the pattern changes as my distance from me to the wall changes? That's length. Okay, right here. And just set the next second set of hands here. From there to there, that's x. These are your x values right here between the fringes. Does that make sense? And then your length is how far away from the wall you're projecting something. Okay. So anyways, get back to this example. Length is going to be 4 meters away. So then the question is, well, what is your x value? Or sorry, what is your d value? I put those backwards, didn't I? Sorry. This one right here is supposed to be that one. That's x. D is the one I screwed up on. D is the distance between your slits. Now, if I don't tell you the distance between the slits, but I tell you that there's 1,000 lines per centimeter, we take the reciprocal of that. So if there are 1,000 lines in 1 centimeter, then if you take the reciprocal of this, then it means that there's 1 line in every 1,000th of a centimeter, right? Like 1/1,000th of a centimeter is how far apart the lines are. So basically what I'm saying we need to do is we need to make this 1/1,000. To the -2 though, because it's still in centimeters. All you have to do is if I give you the lines per centimeter, you take the reciprocal of it and make it 1/1,000th of a centimeter. That's it. So 1/1,000th of a centimeter is how far apart each of those little slits are. And then now you solve this. I'm sorry guys, I'm making a mess out of this slide. I'm trying to rush at the end of class. I always do worse when I rush. So your x value was actually the 19.2 times 10 to the -2. Your d value is 1/1,000th, but you got to make it to the -2 because it was in centimeters. You're dividing by 1 and dividing by 4. I got 0.0048. No? You got 0.0048? Okay. One over 1,000 to the -2. To the -2. Make the to the -2 after the 1 over 1,000. Make that be after. Like put this in brackets. Make it 1 over 1,000, and then make it go to the -2. That could be an issue. Times it by 19.2 to the -2 over 1 over 4. You get a different one? You get 4.8? Let me try mine one more time then. Okay, 1 over 1,000. Make that go to the -2. Oh goodness, come on, Chris. Answer to the -2. Okay, then I'm timesing that by 19.2 to the -2. Dividing it by 1 and 4. Ooh, okay, I got something different. 4.8 to the -7? Okay, there we go. Thanks for making me stop. I must have screwed up. Okay, 4.8 to the -7. Okay, this actually makes more sense than my first answer, because this would make it 480 nanometers. If you're wondering how I did that in my head, I took the decimal place and moved it over twice, made it 480 to the -9, and then a -9 is a nanometer. So this would actually make a lot of sense, because that's probably about purple light. So, okay, sorry, I'm getting to the end of class, and I'm rushing, and I'm always making mistakes when I rush. Do you guys have questions that you can think of right now? Okay, you're catching my mistakes, so that's good news. Okay, let's wrap this up, because I think I'm done with my math examples. There is a third observation that really proved that light was a wave. And if you guys remember the name Maxwell, James Maxwell, he predicted that light was a wave, and he thought it was a transverse wave. And if you don't remember the difference between transverse and longitudinal from Physics 20, here's a nice little visual idea. Transverse waves are waves that we believe would then go up and down. And if it's actually a physical wave, a mechanical wave, you can actually see it go up and down. Whereas longitudinal waves are like pulses. Sound comes out in pulses like this. So Maxwell believed that light behaved as a transverse wave, but he had no evidence of it. What he then figured out how to do was to set up these little gratings where it's very, very, very thin. And rather than having a double slit, he had a single slit. And what it is, he set up one so that it could polarize light. You ever heard of the phrase polarized sunglasses? What polarized sunglasses do is they have a whole bunch of slits that are like this, that only let light go through if it goes in an up and down component, but it actually filters some of the light out. And I've got some photos here that kind of explain this. In theory, light then goes in all directions. It goes out this way, 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 it goes out this way. It goes in 360 degrees. And as light goes through your polarized sunglasses, there's little gratings in here basically. And those gratings only let one certain orientation of light through. And I think this photo here is the best one. This would be a diagram of what we believe light would do if it's got that wave property to it. it's going up and down and up and down. But it's also going like slightly in, slightly out. And it's got 360 degrees of waves going through it. But if you polarize light and put it through a filter, only one orientation of the wave can pass through because the rest would get blocked. Does this picture kind of help explain the idea? And here's what proved it then. If you then took one filter and put it completely vertical, and you took one filter and put it completely horizontal, in theory, no light would be able to get through. Because here you have 360 degrees worth of rotations available. Then through this one filter, only the completely vertical one goes through. Put the other filter here and it blocks it. Yeah. Really? Cool, I gotta look into that. I've never heard of that before. I'm gonna research that. So here's where I wanna finish class, because I more or less talked about what I want to. I have a few of these that you guys can try. These are polarized light filters. And if you were to look at the light that comes from there, it's basically there's a wave that's coming like this. There's a wave that's going like this. There's a wave that's going like this, right? They're going in all directions. If I put this up there, it filters out most of the light, right? Maybe if you could think of it this way, if there's 360 degrees in a circle, 359 of those degrees are filtered out, and only one of them gets through, right? So there's less light. Take a second one of these, though, turn it sideways, and you actually shouldn't be able to see any light come through anymore. Because what it's done is it's blocked all but this direction. And then if you put this one in sideways, well, then only this direction could get through. So feel free to try this if you'd like. But this was the third piece of evidence then that proved that light must behave as a wave, because we're actually able to block it only using basically a filter like this. So Abel, what did you suggest if we use 3 of them then? Then what happens? Interesting. And are they in like if this one is vertical, that one's horizontal? What do I do for the third one, do you know? Interesting. Well, I've got a whole bunch of slides here. Guys, I'm basically done class. You can mess around with this if you like, because I've more or less covered what I need to. But come experiment, give it a try. So I think I've described more or less all I need to for the day. Yeah, you guys can follow the rest of the pictures. So tomorrow we're going to do a lab where you guys can try some of this on your own as well. So that's all I've got. If you guys want to mess around, go ahead. Otherwise, take off, and we'll talk tomorrow again.